Picture a scene from the early 1980s in the American heartland. You are driving down this dusty county road, right? And on your left, there is a hand-painted wooden sign hammered into the front lawn of a multi-generational family farm.
Let me guess. An auction notice.
Exactly, an auction notice. The bank has foreclosed, the tractors, the silos, the land itself. Everything is being sold off for pennies on the dollar because of the absolute worst financial agricultural crisis since the Great Depression. Blood is essentially in the water.
Right. It was a bleak time.
It really was.
Yeah.
But then, you look out the passenger window to your right across the highway, and on a neighboring farm, cutting through the twilight, is this glowing, high-intensity red laser beam sweeping across a massive field.
Just a completely surreal image.
Yeah, it's guiding a gargantuan 475 horsepower earth-moving machine that's equipped with, aerospace-grade microelectronics.
It is a profound, almost jarring visual contradiction. You have total financial ruin on one side of the road and million-dollar sci-fi technological investments on the other.
And welcome to this custom-tailored deep dive. Today, we are pulling back the curtain on the 1980s agricultural land leveling revolution. And the mission for this deep dive, well, it's to unpack that exact fascinating paradox.
It's a big one.
It is. How did an era defined by mass bankruptcies, plummeting crop prices, and economic terror become the exact same era where American farmers universally adopted spinning laser beams to mathematically re-engineer the surface of the earth?
Well, the answer weaves together macroeconomics, catastrophic environmental failures, strict water legislation, and honestly pure brute force engineering.
Which is wild.
It really is. We were looking at a 10-year window where the American farmer had to fundamentally pivot from being a steward of natural topography to becoming basically a geospatial engineer.
And we are going to explore how we got there, the unbelievable toll it took on the soil, and why this invisible revolution still dictates how we grow food and manage water today. So, okay, let's unpack this. To really understand why farmers started buying lasers, we have to talk about the financial meat grinder of the early 80s.
We absolutely do, because you cannot separate the technology from the economic terror of that decade. To grasp the mindset of the farmer in 1982, we have to look briefly at the decade right before it.
The 70s.
Right. The 1970s were an agricultural gold rush. We had a massive surge in global export demands, largely driven by grain sales to the Soviet Union. Inflation was running hot, which meant the value of physical assets, like farmland, were skyrocketing.
Right. The government was basically telling farmers to plant fencer to fence row.
Exactly. Agricultural economists and even federal policymakers were actively encouraging farmers to borrow heavily against the rapidly inflating value of their land.
Because the land was worth so much on paper.
Yeah. So they took out massive loans to buy more acreage, buy bigger tractors, expand their operations. It was a classic debt-fueled speculative bubble. And then, well, the music stopped violently.
The Volcker shock.
Yes. In 1979, the Federal Reserve, under Chairman Paul Volcker, decided they had to break the back of double-digit national inflation. To do that, they aggressively tightened the money supply. The federal funds rate, the baseline interest rate for the whole economy was pushed all the way to 20%.
Wait, 20%, which means the interest rates on standard operating loans for farmers went even higher.
Much higher. Farm loan rates peaked at 21.5%.
Put yourself in the boots of a struggling family farmer for a second. You listening right now, imagine trying to run a business where your operating loans carry a 21.5% interest rate. You aren't just paying back what you borrowed. A fifth of your total debt is being added on top every single year just to service the loan.
It completely paralyzed the industry. Total farm debt reached an astounding $215 billion by 1984.
Wow.
But here is the truly catastrophic part. Because interest rates were so high, no one wanted to borrow money to buy land. And because no one was buying land, the value of the land completely collapsed.
And that land was the collateral holding up the entire house of cards.
Precisely. In Iowa, for example, farmland lost roughly 60% of its value between 1981 and 1986.
60%.
Yeah. Nationally, the average value dropped by a quarter. So suddenly, a farmer who borrowed $500,000 against $1 million farm woke up to find their farm was only worth $400,000. They were underwater.
So the local agricultural banks began calling in the loans, right?
Exactly. And when the farmers couldn't pay, the banks began foreclosing. We are talking about hundreds of thousands of family farmers defaulting.
So we have cratering land values, 21% interest rates, and on top of that, crop prices are in the basement because of the 1980 Soviet grain embargo. The math is horrifying.
It is.
And yet this is the exact moment when custom contractors start driving up to these struggling farms, offering to bring in massive heavy equipment to perfectly flatten their fields with lasers, and they are charging a fortune for it, up to $500 an acre.
Which brings us back to the paradox. While the small to medium family farms were entirely frozen out of credit markets and desperately trying to hold on to their land, well-capitalized corporate operations and large family mega farms were aggressively hiring these laser-leveling contractors.
I have to push back on the logic there, though. So to save a farm from a debt crisis, you take on a massive capital expenditure. You essentially buy space-age construction services to save money.
I know how it sounds.
It's like buying a brand new Ferrari just because you want to save a few dollars on your gas commute to work. It doesn't make sense on the surface.
It seems utterly counterintuitive until you sit down and look at the net present value, or NPV, formulas that agricultural economists were publishing in trade journals at the time.
Okay.
When commodity prices collapse, your profit margins compress to almost zero. In that environment, the only way a farm survives is by ruthlessly cutting its variable operating costs. And in irrigated agriculture, the two biggest variable costs are water and the diesel fuel required to pump that water out of the ground.
Okay, let's break down the NPV concept, because that's the key. Net present value is basically a way of calculating if a big expense today is actually going to be profitable in the long run, factoring in the time value of money, right?
Exactly. The NPV formula looks at the initial capital investment, that $150 to $500 per acre you pay the earth-moving contractor, and weighs it against the future annual savings.
Right.
And even when the economists applied a massive discount rate to account for those crushing 20% interest rates, the laser leveling investment paid for itself incredibly fast, sometimes in just 3 or 4 years.
Because of the efficiency. I mean, if a field has a natural rolling slope and you try to flood it with irrigation water, the water pools in the low spots and starves the high spots. You have to run the diesel pump for days just to make sure the high spots get a drink.
Exactly. You are pumping millions of excess gallons of water, burning thousands of gallons of diesel fuel. But by using a laser to shave the earth down to a mathematically perfect uniform grade, farmers reduce their water application times by up to 50%.
50%.
Yeah. The water just sheets evenly and rapidly across the entire field. That instantly chopped their diesel fuel bills in half.
And the crops themselves respond to that perfect environment.
They do. Because the water distribution is uniform across the entire field, the seeds germinate evenly, the fertilizer doesn't wash away into the low spots, and the crop matures at the exact same time.
That makes sense.
Early adopters of this laser technology were realizing between 17 and 22% higher per acre crop yields. When you combine higher yields with drastically lower fuel costs, it translated into 19 to 27% higher overall profit margins compared to the farmers who didn't level their land.
But here's the tragedy of that efficiency. You just said the high capital costs were up to $500 an acre. If you are a traditional 160-acre family farm, drowning in debt, the bank isn't going to loan you another $80,000 to hire a laser contractor. You are locked out of the revolution.
And this is why the laser leveling era actively accelerated the consolidation of the American farm. The technology heavily favored economies of scale. Large corporate farms had the cash reserves or the credit lines to re-engineer the earth. Smaller farms did not.
You just couldn't keep up.
No, they couldn't compete with the new efficiency baseline, and many were absorbed by the larger operations.
There was also a massive legislative shift right at this moment that fundamentally altered the economy of scale in favor of those massive operations. The 1982 Reclamation Reform Act.
Oh, that act was a watershed moment.
Yeah.
Since 1902, federal reclamation law had dictated that highly subsidized federal project water, the water from massive dams and reservoirs out west, could only be delivered to farms that were no larger than 160 acres.
Which was originally designed to promote the small family farm and prevent massive land monopolies.
Right. But in 1982, they changed the rules.
They did. The 1982 Reclamation Reform Act officially increased that acreage limit from 160 acres to 960 acres.
That is a staggering jump.
It is. So suddenly a farming corporation could consolidate almost 1,000 acres of land, still receive heavily subsidized water, and easily justify the massive capital expenditure of buying their own laser leveling tractors. I mean, a 960-acre farm can amortize the cost of a $100,000 laser system a lot faster than a 160-acre farm.
It fundamentally shifted the baseline of what it meant to be a commercial farmer. But if we want to understand why those efficiency gains were so hypercritical, we have to look beyond just the diesel fuel savings.
Right.
Because in many parts of the country, laser leveling wasn't just a smart financial move. It was the only way to stay out of jail or to prevent the physical earth from collapsing beneath your feet.
Yeah, the legislative hammer drops. Because while the Midwest was dealing with the financial crisis, the American West was dealing with a massive hydrological crisis. We are talking about state water laws that were so strict, they practically mandated the use of lasers by law.
Nowhere was this transition more abrupt and severe than in Arizona. In 1980, the state passed the landmark Groundwater Management Act, commonly referred to as the GMA.
And this wasn't passed just to be environmentally friendly, right?
Yeah. It was passed out of sheer existential panic.
Absolute panic. Arizona was experiencing catastrophic aquifer overdrafts. Farmers and cities had been pumping so much groundwater out of the subterranean aquifers that the physical land above them was sinking.
Subsidence. I want to pause on this because the concept of subsidence is terrifying when you really think about it. We are talking about a pothole in the road. In some areas of Arizona, like the town of Eloy, the ground had subsided by 12.5 feet over the previous decade.
Right.
The actual elevation of the earth dropped over 12 feet because they sucked so much water out from underneath it.
To understand how that happens, you have to picture the aquifer not as an underground lake, but as a rigid sponge made of gravel, sand, and clay.
The water fills the empty spaces in that sponge, and the hydraulic pressure of that water actually helps hold up the weight of the dirt above it.
But when you run a massive diesel pump day and night and you drain the water out of the sponge faster than the rain can refill
The
it,
sponge dries out, and the sheer weight of the earth above it crushes those empty spaces flat. The ground collapses. And once that clay and gravel is compacted, it can never hold water again. The storage capacity is permanently destroyed.
and a 12-foot drop completely destroys human infrastructure. I mean, if you have a concrete gravity flow irrigation canal that relies on a very precise, gentle slope to move water across a county, and the ground underneath the middle of that canal suddenly drops 12 feet, the concrete shatters.
Exactly.
The water flows backward, roads buckle.
It is a geotechnical nightmare. So the 1980 Arizona GMA stepped in with unprecedented authority. The law established active management areas, or AMAs, covering the most heavily populated and farmed regions.
And what was the goal there?
The ultimate goal of these AMAs was safe yield, which is exactly what it sounds like. It's a legal mandate that the state cannot pump more groundwater than is naturally or artificially recharged back into the aquifer.
But how do you enforce that on a farmer who has been pumping whatever he wants for 50 years?
The state enforced it through incredibly strict water duties. The Department of Water Resources calculated exactly how much water a specific crop, like cotton, theoretically needed to grow in a specific soil type, assuming maximum irrigation efficiency. They then capped the farmer's legal water right at that exact number.
So if you were a cotton farmer in Pinal County, Arizona, the state essentially said you get 3 acre-feet of water per acre and not a drop more.
Exactly.
And if you tried to flood your field the old-fashioned way, over uneven rolling dirt, you would run out of your legal water allotment by August. Your crop would die in the field, or you would be heavily fined.
Right. The law penalized inefficiencies so harshly that you were backed into a corner. The GMA effectively legislated the use of lasers. To meet those stringent state water duty requirements, Arizona farmers had to abandon traditional sloping fields and transition to what are called dead-level basins.
Let's define a dead-level basin for you listening. How flat are we talking?
A dead-level basin means the field is engineered to have a slope of less than 0.2 feet over a quarter-mile run.
0.2 of a foot of variation over 1,300 feet of dirt. That is a practically zero slope. You simply cannot achieve that by eyeballing it from the seat of a tractor.
You cannot. And the panic wasn't limited to Arizona. Over in California, the state was hit by an absolutely catastrophic drought stretching from 1987 to 1992.
When the surface water from the mountains dries up in California, the farmers instantly pivot to pumping groundwater to save their orchards and crops.
And that extreme pumping triggered the exact same massive subsidence in the Central Valley that Arizona experienced. The ground sank so severely that it began to physically threaten the structural integrity of the California aqueduct.
The massive concrete river that transports water from Northern California down to Los Angeles.
Yes, Land leveling shifted from an agronomic decision to a vital necessity to prevent the physical collapse of the state's hydrology network.
And the desperation was so high that it led to one of the most unbelievable financial arrangements I've ever heard of. The 1988 agreement between the Imperial Irrigation District and the Metropolitan Water District of Southern California.
Oh, the IID and the MWD agreement. This is a fascinating moment in the history of resource economics.
Walk us through it.
Okay, so the Imperial Irrigation District is a massive, incredibly productive agricultural zone in the Southern California desert. But they came under intense legal pressure from the State Water Resources Control Board for allegedly wasting water because agricultural runoff was flowing uselessly into the Salton Sea.
Meanwhile, right next door, the Metropolitan Water District, which supplies the drinking water for the massive urban sprawl of Los Angeles, is desperate for water because of the drought.
So they struck a deal. Urban Los Angeles agreed to provide a massive capital injection of $92 million directly to the Imperial Valley farmers.
The people in the city paid $92 million to the farmers in the desert.
Yes, those funds were explicitly used to line dirt canals with concrete and to heavily subsidize precision agricultural land leveling for those Imperial Valley farmers. By using urban capital to pay for the laser earth moving, the farms became vastly more efficient.
To save the water.
Exactly. The goal was to salvage 100,000 acre-feet of water annually, water that was previously wasted as runoff, and transfer that salvaged water to the cities.
It was a revolutionary market-based transfer. The cities needed water, the farmers needed flatland, so the cities bought the farmers the lasers. But there's another example in California that is far darker. It wasn't about saving drinking water, it was about containing a toxic nightmare. The Westlands Water District in the San Joaquin Valley.
The Keisterson Reservoir disaster. This is where laser leveling became a tool for environmental damage control.
Let's break down the mechanics of the Keisterson disaster because it sounds like a sci-fi horror movie. In the Westlands District, the soil geology is unique. They have a shallow, impermeable clay layer sitting just beneath the topsoil. It acts like a concrete floor underground.
Right. And when farmers heavily irrigated those fields, the excess water couldn't drain away deep into the earth. It hit that clay pan and started to fill up the soil profile like a bathtub. As the water table rose, it dissolved naturally occurring salts and trace minerals in the soil, bring them right up into the root zone of the crops, threatening to kill the plants.
And one of those naturally occurring trace elements in the soil was selenium. Now, selenium in tiny amounts is fine, but in high concentrations, it is highly toxic.
Exactly. So to save their crops, the farmers installed underground drain tiles, perforated pipes buried in the soil to capture that toxic salty water and pump it away.
And they pumped it into a massive federal drainage canal that emptied out into the Keisterson Reservoir, which was a sprawling complex of wetland ponds.
But in 1983, wildlife biologists started noticing something horrific at Keisterson. The selenium from the farm runoff was bioaccumulating in the food chain.
Yeah, the results were devastating. They found catastrophic rates of mortality and horrific deformities in the embryos of migratory waterfowl nesting at the reservoir. Birds were hatching with missing eyes, distorted beaks, and missing limbs.
It became a massive national scandal. The federal government stepped in and immediately shut down the drainage facilities. They plugged the pipes.
Which effectively turned the massive Westlands agricultural district into a closed basin. The farmers could no longer drain their toxic water away.
Right. And just to be clear for you listening, we aren't taking a stance on whether these environmental regulations or the water policies were good or bad. We're just impartially reporting on how these laws and events legally forced the farmers' hands.
Exactly. We're looking at the engineering response. Because the only way they could prevent that selenium-laced water table from rising up and killing their crops was through a strategy called source control.
Source control. Meaning, if you can't drain the water out of the bottom of the bathtub, you have to perfectly control exactly how much water you pour into the top.
Right. They had to strictly limit deep percolation. And the only physical way to apply an incredibly precise, minimal amount of water across a massive field without leaving dry spots is to perfectly laser level the land.
They had to create a continuous, flawless slope so water moves swiftly and evenly. It was environmental containment executed via laser-guided tractors.
So we have established the intense economic pressure, the legal mandates, and the environmental disasters driving this need for absolute perfection. But how do they actually do it? Because you cannot achieve a dead-level basin with a tractor and a good guess.
You certainly cannot. Prior to the 1980s, the traditional method for leveling land was relying on an optical transit.
Like surveyors use.
Yeah, a surveyor would stand in the middle of a field looking through a telescope at a wooden rod held by another guy. They would hammer wooden stakes into the ground every 100 feet, mark them with a crayon, and then the tractor operator would drive back and forth, trying to visually match the height of the steel scraper blade to the crayon mark on the stake.
It was slow, it was entirely dependent on human intuition, and it was completely inadequate for the centimeter-level tolerances these new laws required.
It was a mechanical art form, but what the 1980s required was mathematical certainty. To hit centimeter-level accuracy, the agricultural industry had to adopt aerospace technology.
Let's talk about the lasers. How does a beam of light actually control a massive tractor dragging 36 tons of dirt? Walk me through the hardware.
Well, it fundamentally shifted the industry from mechanical intuition to electronic precision. The core principle involves generating a highly stable 360-degree plane of laser light hovering invisibly over the entire field.
Yeah.
It starts with a transmitter, which is a device mounted on a stationary tripod, usually positioned at the highest point of the field or at the edge to avoid the dust of the tractors.
And what is happening inside that transponder box?
Inside, a laser diode or gas tube generates a beam. But it can't just be a normal beam, it has to be a collimated laser beam.
Let's define collimated for a second. That basically means the light waves are traveling perfectly parallel to each other, right? They don't spread out like the cone of light from a flashlight.
Exactly. If the beam spread out, it would be toothed through a receiver. A tall, vertical electromotive mast is bolted directly to the frame of the tractor's scraper. You know, the heavy steel implement pulled behind the tractor that actually cuts into the earth. The receiver is mounted at the top of this mast, protruding up into that invisible plane of laser light.
And what does the receiver do?
The receiver contains a vertical array of highly sensitive photocells. Its only job is to detect exactly where that sweeping laser beam hits it. If the beam hits the top photocells, the receiver knows the scraper is too low. If the beam hits the bottom photocells, it knows the scraper is too high.
And how accurate is this?
We are talking about detecting a beam of light up to 300 meters away with an accuracy of 10 millimeters.
10 millimeters, that's less than half an inch of variation across 3 football fields of dusty, bouncing farm ground. That is wild precision.
It is. Now, the receiver translates those light hits into electrical signals and sends them down a cable to a control box mounted inside the tractor cab right next to the operator. That control box is the computational hub. It instantly processes the signal and sends an electrical command directly to the tractor's hydraulic valves.
And the hydraulic valves control the massive cylinders that physically raise or lower the steel scraper blade. So the laser talks to the receiver talks to the box talks to the hydraulics, and the blade adjusts automatically, completely bypassing the human operator's visual estimation.
That is the complete feedback loop. But here's where we need to dive deep into the mechanical realities of the 1980s, specifically regarding those hydraulic valves. Because when we think of computer-controlled machinery today, we expect smooth, seamless, gradual adjustments.
Right. If you are using cruise control on a modern car, it gently rolls onto the throttle.
But that is not how the 1980s hydraulic systems worked. True proportional control, where a hydraulic valve opens just a tiny bit if you only need a microscopic adjustment, requires complex computing power and highly sensitive solenoids that were not commercially viable in agriculture until 1998, when Spectra Precision introduced them.
So how did the 80s valves work?
All standard agricultural laser systems in the 1980s utilized what engineers call a bang-bang directional control valve.
A bang-bang valve. I love that engineering term because it described exactly what it does. The valve was completely binary. It was either 100% fully open or 100% violently closed. There was no in-between.
None. It is a crude but effective method.
It's exactly like a heavy-footed teenager learning to drive a manual transmission for the first time. They don't know how to ease into the pedals. They slam the gas pedal to the floor, and then they slam the brake pedal to the floor.
That is a perfect analogy for what was happening inside those hydraulic lines. If the laser receiver detected that the scraper blade was just 1 inch too high, the electrical signal hit the bang-bang valve, and the valve snapped fully open instantly. The heavy steel blade would drop at maximum speed until the receiver hit the designated on-grade deadband zone.
And
The millisecond it hit that zone, the valve slammed completely shut.
And stopping thousands of pounds of moving steel instantly has consequences.
It resulted in extreme fluid hammer within the high-pressure hydraulic lines. The sudden, violent stopping of momentum caused the entire piece of machinery to shudder. It created a very jerky, stepped mechanical motion.
And this caused a phenomenon that the farmers called porpoising. Because the blade dropped so violently fast, the momentum would often carry it past the narrow half-inch on-grade zone. It would overshoot the mark and dig too deep.
Right.
The receiver would instantly panic, realize it was now too low, and slam the valve in the opposite direction to yank the blade back up.
So the massive scraper is literally bounding up and down through the dirt, like a dolphin swimming through the ocean, leaving a wavy, undulating pattern in the soil.
To stop the porpoising, the tractor operators had to become incredibly skilled at managing their forward speed and perfectly balancing the volume of soil they were carrying in the scraper bowl, essentially using the weight of the dirt to dampen the violent reactions of the bang-bang valve.
And we must emphasize the sheer, terrifying scale of the machinery experiencing this mechanical shuddering. These were not the small, friendly red tractors you see in children's books. The sources detail operations like Gaston Tyson's Mer Rouge farms down in Louisiana. For their heavy leveling, they were utilizing a Rome 475C tractor.
The Rome 475C. That is an articulated four-wheel drive Leviathan. It has a 475 horsepower Caterpillar 3408 8-cylinder diesel engine.
And it was pulling a scraper bowl behind it with a capacity of 36 cubic yards of earth in a single pass.
Let's put 36 cubic yards into perspective. A cubic yard of topsoil weighs roughly a ton, sometimes more if it's wet. So that tractor is dragging 36 tons of dirt.
Wow.
Yeah, and the laser control box is slamming a bang-bang valve open and closed, causing 36 tons of dirt and steel to shudder and bounce. The sheer kinetic energy involved is mind-boggling.
It placed immense stress on the structural integrity of the implements. Hoses blew, welds cracked. But despite the mechanical violence of the bang-bang valves and the porpoising, the resulting field grade, when the dust finally settled, was accurate to within millimeters.
So who is actually building the brains of these operations? Because out in the fields, it was John Deere, Caterpillar, and Rome, but they didn't make the lasers. This sparked a massive corporate arms race between tech companies trying to capture the agricultural market.
It did. The two undisputed titans of the 1980s agricultural laser market, the companies whose logos were on every tripod and control box, were Spectra Physics and Laser Alignment, Inc.
Let's look at Spectra Physics first. Their headquarters were in Dayton, Ohio.
Originally, the foundational technology was developed in Dayton by two engineers, Robert Studebaker and Ted Teach, who formed a company called Laserplane Corporation in the late 1960s. They were the absolute pioneers of agricultural laser control.
Right.
But in 1976, their operation was acquired by Spectra Physics, and the integration was fully consolidated by 1982.
And Spectra Physics was not a farm equipment company. They were a massive high-tech photonics corporation based out west. They built industrial lasers, scientific lasers for universities, barcode scanner. So you had this massive infusion of aerospace-grade photonics capital slammed directly into the dirt and diesel world of Midwest agriculture.
That acquisition brought immense manufacturing scale and research capital to the sector. Spectra Physics dominated the market with incredibly robust, highly engineered models. In 1981, they introduced the EL1, which they proudly marketed as the world's first electronic level.
Why was the electronic part such a big deal? What were they using before?
Before the solid-state electronic levels, the early lasers relied heavily on fragile helium neon, or Hine, gas plasma tubes to generate the beam.
Wait, a glass tube filled with glowing plasma, mounted on a tripod in the middle of a dusty field with 475 horsepower tractors rumbling past it.
Yes, they had to heavily shock mount the glass tubes inside the transmitters. They were incredibly delicate, the power supplies were bulky, and the gas tubes usually only lasted a few hundred hours before they burned out and had to be replaced. It was highly temperamental technology.
I just marvel at that contrast. You have a 1980s farmer dealing with 21% interest rates, wearing denim and a trucker hat, delicately adjusting a highly sensitive helium neon plasma laser straight out of a science fiction laboratory just so he can grow a better crop of cotton.
It is a striking juxtaposition, but the technology rapidly evolved. By 1988, Spectra Physics shifted away from the gas tubes entirely, introducing cone technology solid-state lasers to drastically improve beam quality and durability.
Oh, that's much better.
Yeah. And inside the tractor cab, they utilized the famous CB2 CT0D control box. It was a rugged, dust-proof computer interface that effectively forced the entire earth-moving industry to professionalize its electronics.
But spectrophysics didn't have a monopoly. They had fierce, innovative competition from a company called Laser Alignment, Inc.
Yes, based up in Grand Rapids, Michigan. Laser alignment was a significant innovator, taking a slightly different approach to the user experience. They were renowned for their laser beacon series, specifically the LB1.
And the LB1 was prized because of its rapid setup and ease of use. The earlier lasers required a lot of calibrating and leveling the tripod itself. But the LB1 featured a 10-minute setup time, and more importantly, it allowed for true one-person operation.
Which was a massive labor savings for a struggling family farm. The farmer could drive his pickup truck to the edge of the field, set up the LB1 on the tripod, turn it on, and then walk away. He can just go jump in the tractor and drive all day without needing a second person constantly monitoring and recalibrating the tripod.
Laser alignment continued to push the envelope in the late 80s, eventually releasing the LB4 in 1989. And the LB4 was revolutionary because it was the first commercially available dual-grade rotating laser.
That was a tremendous leap forward. Earlier lasers could slope a field on one axis, say, sloping it downhill from north to south. But a dual-grade laser meant the farmer could program complex compound slopes directly into the transmitter.
So they could tilt it in two directions.
Exactly. You could slope the field slightly north to south and simultaneously slope it slightly east to west. The laser plane itself would tilt on both the X and Y axes.
So having the laser hardware is one thing. You've got the spectrophysics EL1 or the laser alignment LB4 spinning away. But how you actually use that laser, how you decide to sculpt the earth, depends entirely on the geography of where you are standing.
Absolutely.
Farming in the heavy clays of California requires a completely different earth-moving strategy than farming in the swamps of the Mississippi Delta.
The regional strategies highlight how incredibly adaptable this technology had to be. A laser is just a straight line, right? How you apply that line to the dirt changes everything. Let's contrast the California Central Valley with the Mississippi Delta. Even within California itself, you have massive geographic and hydrologic extremes.
In the Sacramento Valley, up in Northern California, you have these incredibly heavy, slow-draining clay soils. It's essentially potting clay, and that makes it perfect for growing rice.
Right, and agronomy dictates that rice requires a continuous, uniform water blanket over the soil to suppress weed growth and protect the fragile seedlings from temperature swings.
So the leveling strategy in the Sacramento Valley was to use lasers to create massive, perfectly flat rectangular checks, or basins. They essentially carved the landscape into a series of giant, flat steps that could hold exactly 5 inches of water from edge to edge.
And to do this, they relied heavily on incredibly wide, long wheelbase implements like the Eversman land planes and huge pole scrapers.
But if you travel just a few hundred miles south into the San Joaquin Valley, the soil profile is completely different. It's alluvial soil.
Right.
Define alluvial soil for us.
Alluvial soil is loose, unconsolidated soil or sediment that has been eroded, reshaped by water, and deposited in a non-marine setting. It's often sandier and drains much faster than clay.
And in the San Joaquin Valley, they aren't growing rice in standing water. They're growing high-value cash crops.
Yeah.
Cotton, vegetables, almonds, and tree nuts, so they don't want a flat bathtub.
Exactly. The primary objective there wasn't holding standing water, it was maintaining precision, continuous slopes. Because it's an arid desert environment, irrigation water naturally brings salts into the soil.
Oh, right.
If that water sits stagnant, the water evaporates, and the toxic salts are left behind in the root zone, eventually poisoning the plants.
So they used the dual-grade lasers to engineer perfectly tilted fields. They needed the irrigation water to move swiftly and continuously down long furrow runs. This prevents the water from percolating too deep and wasting water, while simultaneously leaching those accumulated toxic salts sideways and out of the active root zone.
It was a delicate balancing act of velocity and percolation. And to move that loose, dry desert alluvium, California contractors frequently relied on Miskin brand scrapers.
How are those different?
Unlike the massive single bowls used elsewhere, Miskin scrapers were often pulled in tandem or even triple configurations, a tractor pulling a train of 3 scrapers picking up and dropping dirt continuously across a mile-long run.
Now contrast the delicate slopes of California with the absolute brute force engineering of the Mississippi Delta. We are talking about Arkansas, Mississippi, and Louisiana. The soils there are often heavy, sticky buckshot or gumbo clays, specifically the Sharkey and Alligator soil series.
The delta leveling strategy was totally revolutionized by a specific concept called zero-grade farming.
And this concept was championed by a specific family in Arkansas, the Isbell family.
Yes, Leroy Isbell and his family, operating on their 3,500-acre farm near England, Arkansas. Historically, rice in the delta was grown using a method called contour levees. A farmer would look at the natural, irregular, bumpy elevation of his land and use a tractor to build winding, serpentine dirt walls, the levees that followed the natural topographic contour lines.
It looks like a topographic map drawn in the dirt. It was incredibly inefficient. You couldn't drive a massive combine harvester in a straight line because you had to constantly turn to follow the winding dirt walls. And you lost a massive percentage of your plantable acreage just to the footprint of the dirt levees themselves.
So Leroy Isbell realized that with the advent of the laser, he didn't have to follow the natural contours anymore. He could force the land to be a 0.00% slope, a mathematically perfect horizontal plane.
Zero grade. By eliminating the slope entirely, the Isbells could bulldoze and eliminate all those winding internal levees. They just built straight, geometric perimeter levees around the outside edge of a massive square field.
It maximized the plantable acreage and allowed machinery to operate in perfectly straight lines, saving immense amounts of time and fuel.
I like to use the bathtub analogy for the zero-grade fields. It's literally like turning a 100-acre field into a giant, perfectly flat bathtub. In the spring, you turn on the high-volume irrigation tap at one end. Because the field is laser flat, the water flows in and floods the entire field uniformly to a depth of exactly 4 inches. You grow your rice all summer in that water, but the absolute genius part is what happens when you pull the plug in the fall.
Because the field is perfectly flat and engineered with deep perimeter drainage ditches, it drains instantly and uniformly. There are no low puddles left behind.
And that instant drainage meant Delta farmers could rotate their crops seamlessly. They could grow flooded rice one season, drain it perfectly dry, and rapidly plant furrow-irrigated soybeans or cotton in the exact same field the very next season without having to re-engineer the dirt.
The adoption of the zero-grade strategy in the Delta was radically accelerated by a specific, terrifying climate event. The summer of 1980 brought a catastrophic drought to the Mid-South. We are talking about 2 consecutive months of 100-degree Fahrenheit heat with absolutely zero rain.
It decimated the region. There is a story about the Sullivan family farm in Mississippi County, Arkansas. They had a massive farming operation, thousands of acres. But the heat and the drought destroyed almost everything they planted.
Right. The only acreage on their entire massive farm that actually survived and produced a harvestable crop that year was a single 80-acre parcel that they had experimentally precision-leveled and irrigated prior to the drought.
That one 80-acre patch survived while everything else withered. That drought proved definitively to the Delta farmers that unleveled land in an extreme climate event was an existential liability. It forced a regional paradigm shift. If you wanted your family farm to survive the next drought, you had to call the laser contractors.
But, and this is a massive but, dragging 36 cubic yards of topsoil back and forth across a field has brutal, unintended, and often devastating consequences for the soil itself. We need to talk about the agronomic toll, because it wasn't all just higher yields and neatly saved water.
Right, we have to look at the collateral damage. Because making a field flat is a violently traumatic process for the local ecosystem. The most immediate biological impact is something agronomists call the cut-and-fill yield gap.
To make a naturally rolling field mathematically flat, the scraper blade has to shave the dirt off the top of the high spots, which is called the cut area, and carry that dirt to dump it into the low spots, which is the fill area.
And the problem is, the soil is not a uniform sponge all the way down. The very top layer of the earth is the AP horizon.
The AP horizon is essentially the topsoil. It is the biological engine of the earth. It contains the organic matter, the decomposed plant material, the beneficial microbes, and the readily available nutrients that a seed needs to grow.
But when that heavy scraper blade comes through to take 2 feet off the top of a hill, it completely removes that entire biological engine. It scrapes the AP horizon away and dumps it at the other end of the field. And what is left exposed in those cut areas is the raw subsoil.
And the subsoil is generally a hostile environment for a fragile seedling. It is highly compacted, often contains heavy clays, and possesses very poor chemical properties compared to the topsoil.
When you expose that subsoil, the chemistry of the field goes haywire. In both the Delta and California, dragging the topsoil away led to severe, immediate nutrient deficiencies, particularly with zinc and phosphorus. The pH levels of the exposed subsoil would spike, creating highly alkaline zones.
The zinc deficiency was particularly devastating for the rice farmers. Zinc is an essential micronutrient for the enzymatic processes in a rice plant. If the soil zinc concentration in those severe cut zones fell below zero point 0.5 parts per million, the rice seedlings would suffer catastrophic stunting.
They call it bronzing. The leaves turn brown, the roots stop growing. If a cool weather front rolled in while the seedlings were in that weakened state, a farmer could suffer total stand loss in the cut zones. The seeds would just sit in the dirt and die.
But to combat this, farmers were forced to artificially chemically remediate the trauma they had just caused with the bulldozers. The standard agronomic recommendation became immediately broadcasting large amounts of commercial fertilizer.
How much are we talking?
They were applying up to 40 pounds of phosphorus and anywhere from 2 to 16 pounds per acre of actual elemental zinc directly to the freshly leveled earth, just to restore the baseline productivity they had before they brought the laser in.
It's crazy. You spend a fortune to fix the water flow, but you break the soil chemistry in the process. And it wasn't just chemical damage, it was immense physical damage. Soil compaction.
We talked earlier about those fully loaded scrapers. A tractor and a scraper carrying 36 cubic yards of soil can weigh upwards of 100,000 pounds.
The sheer ground pressure of those massive rubber tires repeatedly driving back and forth over the exact same field, pass after pass, physically crushed the pore space of the soil.
It created severe traffic pans or plow pans. Imagine a layer of soil, usually 10 to 14 inches below the surface, that has been compressed so tightly by the weight of the machinery that it essentially becomes the density of soft concrete.
And the roots of a corn plant or a cotton plant cannot punch through concrete. And more importantly, water cannot soak through it.
Which brings us to the ultimate agronomic irony of the land leveling revolution. Farmers spent hundreds of thousands of dollars to perfectly flatten a field to improve water infiltration and flow, only to compact the underlying soil so severely that the water couldn't actually soak into the ground. It would just sit on top of the traffic pan.
So how do you fix a traffic pan that spans a 500-acre field?
Mechanical remediation. Following the laser scrapers, farmers had to bring in a completely different set of massive, heavy implements called subsoilers.
Implements like the massive Marvin Land Plains 630V or the Rome 4TAC 6000.
These were huge, heavy steel toolbars equipped with massive, curved metal shanks. The tractors would drop these shanks deep into the earth and drag them forcefully through the field to deep rip the ground.
They were ripping the earth 12 to 24 inches deep, physically fracturing and shattering that compacted traffic pan layer just to restore the internal soil structure and drainage that they had just destroyed with the scrapers. You perfectly flatten it with a laser, chemically treat it with zinc, and then violently rip it back open with steel shanks just so a seed can survive.
It was a cycle of mechanical destruction and artificial remediation. And we cannot ignore the broader environmental pollution that this cycle generated.
The externalities. Because what happens on the field doesn't stay on the field. Let's look at the air quality first. In the incredibly dry California Central Valley, during the heat of the summer, running fleets of scrapers across dry dirt generated massive dust plumes.
Specifically, it generated hundreds of tons of PM10 airborne particulate matter.
Let's define PM10 for a moment. It stands for particulate matter that is 10 micrometers or less in diameter. That is incredibly fine dust. It's so small that when you breathe it in, it bypasses the natural defenses in your nose and throat and gets lodged deep in your lungs.
It is a severe respiratory hazard, and the massive earth-moving operations of the 1980s were a significant, documented contributor to the severe regional air quality degradation in the San Joaquin Valley.
So in the dry climates, you had air pollution. But in the wet environments, like the Louisiana coastal prairies, you had severe water pollution caused by a practice called mudding in.
Yes, down at the agricultural experiment stations in Crowley and throughout southwest Louisiana, they faced a unique challenge. After precision leveling a field, the soil was often left cloddy and uneven. A common traditional seedbed preparation involved flooding that recently precision-leveled field with a few inches of water and then running tractors, pulling heavy disc harrows directly through the mud and standing water.
It's exactly what it sounds like. They were using the steel discs to churn the soil and the water into a thick suspended slurry like chocolate milk. The goal was to smooth out the tiny microdepressions and create a perfectly soft mudbed for water-seeding rice from airplanes.
But the resulting runoff was highly toxic to the local waterways. When they eventually drained that chocolate milk water off the field and into the local bayous and rivers, they were discharging massive amounts of topsoil.
Water quality modeling from the era showed that an estimated 85% of the non-point source pollution from rice fields in that specific region, which was mostly total suspended solids, literal dirt, and the agricultural fertilizers chemically bound to that dirt, came from those specific spring discharges immediately following a leveling and mudding in operation. They were flushing their topsoil directly into the rivers.
The physical trauma to the landscape wasn't just limited to soil chemistry and water quality. The massive, unrestrained earth-moving projects of the 1980s fundamentally altered the broader biological ecosystem, and eventually, it aggressively clashed with federal law.
Which brings us to the unintended consequences of the revolution. Let's look at the wildlife first, because it's actually a fascinating, complex paradox. We just talked about pollution killing fish, but in some very specific cases, these mathematically flat, laser-leveled fields became absolutely vital, life-saving artificial habitats.
They did. As the natural wetlands of California and the Mississippi Delta were being drained and plowed under for agriculture, the migrating wildlife had nowhere to go. But a precision laser-leveled rice field, when flooded with a few inches of water in the winter, perfectly mimics a natural shallow wetland.
In California, the conservation footprint of precision-leveled, winter-flooded rice was estimated at approximately 500,000 acres. Because the lasers allowed the fields to be flooded at highly precise, uniform depths across massive areas, it created the perfect wading depths for millions of birds migrating down the Pacific Flyway.
It wasn't just birds. Threatened reptile species, like the giant garter snake, became heavily reliant on the artificial hydrology of the rice fields, utilizing an estimated 80,000 acres of flooded, leveled land for their survival as their natural marshlands disappeared.
And down in the Mississippi Delta, conservation groups actually began actively promoting land leveling. Ducks Unlimited, the massive waterfowl conservation organization, launched a specific project in the late 1980s that paid farmers to convert their rolling corn or soybean fields into precision zero-grade rice fields.
They realized that a leveled, flooded field attracted waterfowl back to the region, and it actively reduced the export of topsoil into the water supply compared to traditional sloping fields.
It was a rare alignment where agricultural efficiency inadvertently served ecological conservation. But while the waterfowl thrived on the new flat Earth, the human historical record beneath that Earth was frequently obliterated.
The archaeology. Because when you are dragging a 36-yard scraper whose blade drops 2 feet into the subsoil across the delta, you aren't just moving dirt, you are moving history. You are bulldozing indigenous settlements that have been buried for centuries.
The 1980s saw a massive growing conflict between the land-leveling contractors who were rushing to save farms from bankruptcy and the state archaeologists who were desperately trying to preserve the historical record.
In Arkansas, along the Languille River, there was a massive survey in the late 1980s. Archaeologists had to frantically race ahead of the bulldozers to recover over 60,000 artifacts from ancient indigenous sites that were directly in the path of agricultural channel clearing and laser leveling operations.
Similar emergency archaeological salvage efforts were forced to occur down in Vermilion Parish, Louisiana. It highlighted a severe, unresolvable tension between rapid agricultural modernization and historic preservation. Once the scraper blade hits an ancient hearth or a burial site, that context is destroyed forever.
But the ultimate wall that the land leveling industry hit in the 1980s wasn't an archaeological site, it was a legislative brick wall, the 1985 Farm Bill.
The Food Security Act of 1985 is arguably one of the most important pieces of environmental legislation in agricultural history. It fundamentally changed the American farmer's relationship with the wild landscape.
Right. Prior to 1985, a farmer could buy a bulldozer, drain a natural wetland, laser level it into a flat square, plant corn, and still receive full federal agricultural price supports for that crop.
And we have to remember the context we established at the beginning. During the crushing 20% interest rates of the farm crisis, those federal subsidy checks were literally the only thing keeping most of these farms out of bankruptcy. They were the lifeblood of the rural economy.
Exactly. The government had incredible leverage. So the 1985 Farm Bill introduced a concept called conservation compliance. Specifically, it introduced the Swamp Buster and Sod Buster provisions. This explicitly legally linked a farmer's eligibility for all federal farm benefits, price supports, disaster payments, crop insurance, and crucially, federal loans directly to their environmental stewardship.
The government basically said, if you want our money to survive the crisis, you have to play by our environmental rules. If you take your laser and your scraper and you level a federally protected wetland after December 23, 1985, you lose every single penny of your federal funding.
It was an incredible financial threat. It set up a massive legal and cultural showdown between the farmers' desire to expand and the government's mandate to protect the environment. And again, impartially speaking, this tension culminated in a landmark 1986 federal court case, United States versus Acres.
The Acres case is fascinating because of how the court interpreted the physical act of using a tractor. Walk us through what happened.
In the Acres case, a California farmer was engaging in that exact deep ripping practice we discussed earlier. He was pulling massive metal shanks behind a tractor through the soil of seasonal wetlands, trying to fracture the hard pan to prepare the land for laser leveling and eventually planting orchards.
He wasn't dumping toxic chemicals. He was literally just dragging a piece of steel through the dirt.
But the federal court ruled that under Section 404 of the Clean Water Act, this specific act of deep ripping fundamentally altered the natural hydrological regime of the wetland. Therefore, the court legally classified the tractor's plow as a point source, and the act of ripping the soil was legally defined as discharging pollutants, specifically the dirt and rock being churned up into the waters of the United States.
That is a massive legal precedent. Using a bulldozer to plow soil was legally defined as discharging a pollutant, which meant it required a complex, expensive federal permit from the Army Corps of Engineers.
Yes, and it sent a shockwave through the agricultural contracting industry. It established the absolute precedent that precision leveling of low-lying natural areas could trigger strict federal intervention if it converted wetlands.
So what was the result of this legislative and legal wall dropping on the farmers? They had the lasers, they had the massive roam tractors, but they were legally boxed in.
It forced a massive permanent pivot in the industry. Instead of utilizing these spectrophysics lasers and enormous earth movers to continuously expand the agricultural frontier outward into wildlands and swamps, farmers were forced to turn their lasers inward.
They couldn't expand, so they optimized.
Exactly. They spent the late 1980s and the decades that followed re-leveling, meticulously maintaining, and hyper-optimizing the fields they had already historically cleared. The frontier was closed. The era of optimization had begun.
Which brings our journey to a close. To recap this incredible, turbulent decade, we saw how the crushing 21.5% interest rates of the Volcker shock, combined with catastrophic droughts and terrifying state water laws like the Arizona GMA, fundamentally forced American farmers to become geospatial engineers.
To survive the economic meat grinder, they had to ruthlessly cut their water and fuel costs. And they achieved that by adopting spinning aerospace laser pentaprisms to turn chaotic, naturally rolling terrain into mathematically perfect plains.
They saved their farms, and they undoubtedly conserved millions of gallons of water in the arid West, but they did it at a brutally high cost to the soil health. They scraped away the biological engine of the AP horizon, requiring massive chemical applications of zinc and phosphorus and severe physical deep ripping just to keep the dirt alive.
It was a period of forced technological maturity, entirely driven by an existential crisis and enabled by the rapid commercialization of precision microelectronics.
But I want to leave you, the listener, with a final thought to ponder, something that builds on everything we've explored today about this massive terraforming project. The entire 1980s laser era, all those bang-bang valves and 36-yard scrapers, was predicated on forcing the Earth to conform to a rigid, artificial, flat plane. Why? Because biologically and hydrologically, that's all a spinning beam of light can project. You can tilt the laser on a dual-grade setup, but it's still fundamentally a flat plane.
It was a two-dimensional mechanical solution applied to a complex, three-dimensional living landscape.
Exactly. We flatten the Earth because our tool is flat. But today, with advanced GPS and GNSS satellite technology, modern tractors can map and sculpt land in true 3D. A tractor today can optimize water drainage by working with the natural topography, rolling over the natural curves of a hill rather than fighting them, slicing them off, and destroying all the topsoil. So here is the ultimate question to chew on. Was the brutal, flat Earth laser leveling of the 1980s a necessary, brilliant stepping stone in the evolution of precision agriculture? Or was it the ultimate act of human hubris, a temporary, violent era where we simply decided it was easier to aggressively flatten the Earth than to develop the computing power to learn how to farm its natural curves?
It is a profound, lingering question of engineering philosophy versus ecological adaptation.
Something to mull over the next time you drive past a perfectly flat, waterlogged rice field or see a tractor kicking up dust on the horizon. Thank you for joining us on this deep dive. Keep exploring, keep questioning, and keep looking at the world a little differently.